I've written a Python script to enable dial-in NETCONF model-driven telemetry to the DevNet iOS XE sandbox. Let's review that code next. Let's start at the iOS XE latest code sandbox. We've used this sandbox many times before. Just be sure to record the hostname, credentials, and NETCONF port number before continuing. Let's get back to the shell. To quickly recap our progress so far, we've customized the ELK stack and deployed it in our ELK instance. We also explored the Yang trees that reveal the metrics we can potentially collect. Let's tie these things together using a Python script. Before we dive in, let's check our pip requirements file. First, we have Python 3 logstash. This package includes Python-based handlers for logstash, the L component in ELK. It's lightweight and simple to use, as you'll soon see. Next, we have XML2dict, which should look familiar. This simplifies converting between XML text and Python dictionary objects. Because NETCONF only uses XML, this is especially useful for us. Last, we have NC Client, which is a popular NETCONF client for Python. We explored NC Client in a previous course on network programmability, but we'll review it again when we encounter it. Let's explore the telemetry.py script to get started. First, we see many import statements. I'll skip NC Client and XML2dict since we just talked about those. First, we import the standard Python logging library. We used this in a previous course for HTTP caching, and in this script, we'll use it to send data to Logstash. The next import pulls in a TCP-based log handler to accomplish this transmission of data. UDP is also an option, but as you know, TCP is reliably transported, so I prefer to use that. The lxml.etree import is somewhat low level, but is necessary when you issue custom RPCs over NETCONF. The fromString functionality allows us to create an XML document from a string, which is what NC Client requires when dispatching RPCs. Now that you understand the packages in play, let's explore the main function. Let's set up the logging first. We create a new logger with a self-explanatory name like netconf mdt and set the logging level to informational. Naturally, you can adjust these values based on your specific use case. In order to use the TCP logstash handler, you must supply 3 parameters. This includes the remote host to which logs should be sent, the TCP port number, and the version. I've set up a public DNS hostname of elk.njrusmc.net for this demo, which is mapped to the ELK instance we built earlier. Port 5045 is the custom TCP port we mapped to the Logstash service in our Docker Compose file. The version parameter relates to the Logstash schema version, and in our case, we use version 1. With those parameters defined, we can create the TCP Logstash handler object by passing them in. The double asterisk, when applied to a dictionary in this context, unpacks the key value pairs and transforms them into keyword arguments. This is a more portable way to supply parameters and is a technique I use often. This new TCP Logstash handler object is added to our existing logger so that anytime we write a log, this handler will be notified. Next, we use our dictionary parameter technique again, except this time for NETCONF connectivity parameters. Most of this data comes straight from the sandbox, so I won't dwell on it. These 3 booleans are specific to SSH transport, and in the interest of staying on topic, I won't dig into them. Effectively, we are telling the SSH transport process to avoid supplying or validating public keys. We want to use simple username-password authentication. The device params option provides platform-specific information to NC Client, which makes the library more resilient on some platforms. The DevNet sandbox runs a CSR 1000V, so we can use CSR to specify that. Finally, we unpack this dictionary passing in the keyword arguments to the manager.connect function. This is wrapped in a with statement, basically a Python context manager, allowing us to access the NETCONF interface through the con variable. Next, we define a list of XML paths, or XPaths, to which we want to subscribe. These are URL-style strings that are based on the Yang models we explored in the previous clip. I'm specifically targeting the CPU 5-second utilization rate, but opting to collect the entire memory statistic list for variety. Next, let's loop over the list of XPaths. The telemetry subscribe function is a helper function that performs the low-level subscription actions. Let's check it out. The function requires the OpenNC client connection, the XPath string, and an optional period. Telemetry subscriptions can be periodic or on change, which is event-driven. In our case, we are only looking at periodic to keep it simple. The default period I am using is 10 seconds. The router expects the period to be specified in centiseconds, or hundredths of a second, hence the value of 1000. Yes, I realize centiseconds are awkward. Cisco didn't ask my opinion when they designed the Yang model. These string variables aren't strictly necessary, but they help keep the code clean. The first string represents the XML namespace for streaming telemetry. Yang push, or YP as I've abbreviated it here, indicates that we want event notifications based on Yang models. In this multi-line F string, we substitute those two variables in, along with several others. This includes the XPath string as well as the period. Once the RPC string has been crafted, we use con.dispatch to send our custom establish subscription RPC to the router. This is where from string comes in handy as it converts our string into the proper XML object that dispatch requires. Once the RPC reply comes back, we simply return it. We can optionally print the raw XML text for troubleshooting by uncommenting this line. More important to us is extracting the data from the RPC reply. Specifically, we need to know if the subscription succeeded or failed. To do that, we convert the XML data into a Python dictionary, then access the text from the subscription result element. The callout shows the structure of an example RPC reply, and we'll dig into it more soon. Now that we have this information, we can test for success. If the string OK appears in the text, we consider it a success, so let's store the subscription ID and print a message to the console indicating so. Otherwise, there was a failure, so let's display the reason. Subscribing to a non-existent group is the most common error I've seen in real life. This is usually due to a typo or a misinterpretation of the Yang model. If that happens to you, double-check your Yang model and XPath strings. At this point, our script runs forever when it enters the while true loop. The con object has a built-in method named takeNotification that hangs until a notification is received. This occurs once every few seconds given our period. Once again, we can optionally print the raw XML result for debugging. To consume the data, we use XML2dict to convert the XML to a Python dictionary, plus we use a post-processor transformation. Let's check out the string2int function quickly. When XML2dict parses a dictionary from the XML data, it assumes all values are strings. As we know from the Yang model, CPU and memory values are unsigned integers, and we need to preserve the integer type so that Kibana can graph it correctly. This function attempts to convert every value to an integer if possible. If not, the original string value is returned. At this point, the message JSON variable should be a dictionary containing the Yang modeled telemetry data. Next, we send a log message to Logstash containing the subscription ID and the entire message itself. Here's an example of what a notification looks like, and once we set up dashboards, we can select individual values from this structure. To aid in troubleshooting, we can print a short one-liner that indicates when notifications are received, along with their timestamps. This helps us locally confirm whether the script is working or not. Okay, I know that was a lot to digest. In the next clip, we'll run the script and explore some of the data structures in greater detail.